Hi everyone, my name is Emily Black, and today I'll be presenting my joint work with Manish, Raghavan, and Solon Barocas on model multiplicity. A growing number of works in the literature have drawn attention to the fact that there are many models available for a given prediction task, which have equivalent accuracy, but differ substantially in other properties, such as fairness, robustness, and interpretability, among others. Aspect of this behavior has been named many different things over the last several years, from the Rashomon effect back in 2001 to predictive multiplicity, leave-one-out unfairness, and underspecification more recently. In this paper, we attempt to unify our understanding of this phenomenon, including going into more detail on how it arises and its technical, legal, and policy consequences. We call this phenomenon of multiple models with equivalent performance existing for the same task, model multiplicity. As we discuss in a few slides, in order to better understand the sources and implication of model multiplicity, under the umbrella of this term, we distinguish between procedural and predictive multiplicity, referring to differences between equally accurate models' internals and predictions, respectively. A lot of work in the fact community takes advantage of this behavior, potentially without even knowing it. The very goal of enforcing fairness constraints on a model at negligible cost to accuracy exploits the existence of model multiplicity. However, this very property, which is so helpful to our community, also presents risks, namely arbitrary decisions and explanations resulting from models. This points to a need to justify model choice beyond accuracy alone. In the paper, we want to be explicit about how opportunities and dangers result from model multiplicity so that we can learn how to take advantage of the benefits that it provides while avoiding its downfalls. In this paper, we present the following contributions. First, a principled understanding of the relationships between model multiplicity, accuracy, and variance. Specifically, we show that model multiplicity can actually increase with accuracy. Secondly, we connect the technical and legal implications of model multiplicity. We do this through a case study of loan decisions and the laws governing them. We argue that model multiplicity may provide more power to the disparate impact doctrine by putting pressure on model developers to search the space of equally accurate models for those with the best fairness properties. Finally, we develop some policy recommendations for taking advantage of model multiplicity while addressing the concerns that it raises. First, we introduce some definitions to lay the groundwork of our paper. We separate model multiplicity into two sub-behaviors to understand its implications. Predictive multiplicity, first introduced by Marx et al., is when several different models built for the same prediction task achieve nearly identical accuracy while having different individual predictions, so different predictions for the same individuals. Meanwhile, procedural multiplicity is when several different models built for the same prediction task achieve nearly identical accuracy while having different model internals. In other words, different internal decision surfaces, which can be understood to mean that they have differences in the process by which a prediction is reached, even if it doesn't impact the final prediction itself. Procedural multiplicity is most often observed when models return different explanations for the same prediction. So where does model multiplicity come from? As prior work has shown, model developers have a lot of decisions to make as they create a model for a given prediction task. And the different choices that they make throughout this creation process, often called the machine learning pipeline, can lead to substantially different models. For example, choices range from what data is chosen within a distribution for a model to train on, feature selection, model type selection, and learning rule selection. And all of these choices, depending on which a model maker chooses, can lead to slightly different models for the same task, which may have equivalent accuracy and often do have equivalent accuracy, but may differ actually in behaviors on other axes, leading to model multiplicity. So there's a lot of evidence for model multiplicity in the machine learning literature. Dong and Rudin, among others, demonstrate that procedural multiplicity exists by showing that models can rely on different sets of features for the same problem and yet achieve the same accuracy. Black et al. And Meher et al. Have shown that deep models with similar accuracies relying on the same features can actually still combine those features in different ways to reach a given output. Recent studies have also provided evidence for predictive multiplicity. Marx et al., who introduced the term, focus on its effects at the individual level, showing that equally accurate models can make different predictions for individuals. And often these models have very seemingly arbitrary differences, such as a change in regularization. And Black et al. Has also shown that such very similar models can also lead to different individual predictions from a change in random seed. And finally, Rodolfo et al. Have demonstrated the effects of predictive multiplicity at the aggregate level, showing that equally accurate models can have different properties, including fairness properties. So now we've seen what model multiplicity is and some evidence of its prevalence. We can now turn to its relationship to accuracy and variance. Our intuition might be that multiplicity will be reduced as the models we build become increasingly accurate. In the limit, this is true. As the error of our best models approaches the Bayes error, we can converge to the Bayes optimal predictor. As a result, it seems natural that our search for more accurate models will naturally reduce multiplicity. Concretely, we might believe that the world looks like this. As accuracy increases, multiplicity decreases. But things are more complex than this. To understand why, we turn to the standard bias variance decompositions of error. We show that multiplicity is tightly related to variance. Thus, any attempts to increase accuracy by decreasing bias and increasing variance will likely lead to more multiplicity, not less. For example, deploying a more complex model class will reduce bias at the cost of increased variance. And even though this can often lead to much more accurate models, it can also lead to increased model multiplicity. Thus, accuracy is not an antidote to model multiplicity, and model selection cannot simply be reduced to accuracy maximization. Instead, we must explicitly consider and deal with multiplicity, beginning with an understanding of the benefits and challenges that it brings. We turn to discussing the benefits and concerns that model multiplicity brings, starting with the opportunities. On an aggregate level, multiplicity shows us that we have the flexibility to choose models among those with equal performance for a given task, which generate the best fairness behavior, whether from the perspective of prediction-based fairness metrics, such as reduced disparity across demographic groups, or procedural ones, such as not using a given feature. In fact, this flexibility might even lead to legal pressure to exploit predictive multiplicity in particular to select the fairest model available among those equally performing for a given context. The disparate impact doctrine, which applies to credit, housing, employment, and some other contexts, states that a model can only treat individuals of different demographic groups differently if the business can demonstrate a legitimate business need for this disparate impact of a model on different groups. In practice, this is often understood to mean that the business has to demonstrate that the disparate impact is necessary to achieve high accuracy. Model multiplicity, however, shows that this is often not the case, which could lead to increased pressure on companies to search the space of well-performing models for the fairest one possible. Multiplicity can also provide the flexibility necessary to improve individuals' experience of model procedures and their outcomes. To illustrate this point in the context of fairness, we explain how procedural and predictive multiplicity can improve a person's capacity to achieve recourse, that is, to obtain a more desirable outcome after receiving an adverse decision. Model developers could exploit procedural multiplicity to find models that exhibit the same degree of accuracy, but differ in the degree to which they rely on features known to be difficult or impossible for people to change. Thus, procedural multiplicity gives model developers a way to take recourse into account into the model development process, as opposed to putting post hoc constraints on recourse-based explanations. Meanwhile, in relevant contexts, predictive multiplicity and predictions from similar models can serve as a natural safeguard against algorithmic monoculture, a phenomenon where all businesses of a certain sector, for example, algorithmic hiring companies, converge on a very similar or the same model. The fear with algorithmic monoculture is that these similar models will generate the same predictions and thus systematically exclude certain individuals by quirks within this model. Inconsistency in model predictions between quite similar models, as has been demonstrated in prior works like Marx et al. And Black et al., and model multiplicity more generally, can thus be helpful in preventing this behavior in relevant contexts. So model multiplicity can serve as a natural bulwark against algorithmic monoculture. Now, while these opportunities are exciting, as we've said, model multiplicity also brings up some concerns. While this flexibility to choose the best possible model from the perspective of fairness exists, without consciously taking advantage of model multiplicity and instead continuing to select models on the basis of performance alone, we run the risk of selecting models which are suboptimal on other axes of performance, such as fairness, both from a procedural perspective, such as choosing a model which uses potentially discriminatory features or using a model with difficult possibilities for recourse, or from a predictive perspective, such as choosing a model with more disparities across demographic groups. A recent paper by D'Amore et al. Shows us that this phenomenon of underspecification leading to suboptimal model behavior on other axes does occur regularly when selecting for models on the basis of accuracy alone. The study most deeply shows this in the context of searching for robust models. Finally, choosing a model based on accuracy alone when multiple models with equivalent performance exist is akin to choosing arbitrarily between more or less favorable outcomes or paths to recourse for certain individuals. Depending on which model is chosen from a variety of equally accurate alternatives, an individual could end up with a completely different outcome as a result of predictive multiplicity or with a much more arduous path to recourse as a result of procedural multiplicity. Model multiplicity brings attention to the fact that in order to fully justify decisions and procedures in high stakes contexts, we have to justify the choice of model as well as a model's internal decision process. And high accuracy may not always serve as a sufficient justification. If we decide between these huge differences on the basis of accuracy alone, which can't distinguish between them, we're effectively choosing arbitrarily between outcomes for individuals. Now, importantly, what we mean by arbitrariness in decisions and explanations here is that the choice between models which determines an individual's outcome is made without thought. With model multiplicity, model makers may not even be aware of the fact that they're making a choice between models that gives individuals such different predictions or explanations. At the very least, justification requires knowledge of the fact that a decision is being made. Randomness, on the other hand, is a different behavior. It's a choice that is purposefully left to chance. Once decision makers are aware of model multiplicity and choose how to deal with it, their randomness that comes from the fact that there are multiple models available for a given task may not always be a problem, as we discussed in the context of algorithmic monoculture. Sometimes having variation in model decisions is good, but the decision to have that variation should be justified. This need for justifiability connects to the law as well. The Fair Credit Reporting Act and the Equal Credit Opportunity Act, or FCRA and ECOA, have various requirements aimed at preventing arbitrariness in decision-making for models determining access to credit, from not including inaccurate or arbitrary information in an individual's credit report to requiring explanations of negative outcomes, in other words, credit refusals from the model. While these laws do not currently call for a justification of the model building process by the letter of the law, a growing number of legal scholars suggest that the spirit of the law calls for such a justification, since to prevent arbitrariness, the choice for why a given model was chosen must be justified as well. To take advantage of the flexibility which model multiplicity affords while creating justifiable decisions, we suggest a policy change in model development in high stakes contexts, namely the creation of a meta rule, increased documentation, and when necessary, model aggregation. First, we recommend the creation of a meta rule, or a full set of criteria for a desired model behavior, potentially beyond accuracy, before model creation. For example, a meta rule might be an accuracy requirement and a fairness requirement, such as low true positive rate differences between demographic groups. This creates a burden to make a well-reasoned choice among potentially equally viable model options before creating a model, thus preventing underspecification and adding to justifiability. In addition, the meta rule and all the choices taken along the machine learning pipeline to create models satisfying this rule should be documented and justified to the extent possible. This documentation of choices, put together with an explanation of how the resulting model functions, ultimately serves as the full justification for why an individual is subject to a given model. However, even taking these steps to reach a justifiable and thus non-arbitrary model will likely still result in many equally viable models for the same task, i.e., they may even all satisfy all of the requirements of the meta rule. Thus, some randomness in the decision-making may remain. As we discussed earlier, in some situations, we may not want to reduce this last layer of randomness in the decision-making process. But in cases where we do, such as government decision processes, we can reduce randomness by aggregating model decisions, for example, by using ensembling to reach the mode prediction over a random sample of models that satisfy the meta rule, as discussed in length at Black et al. Selective ensembling for consistent predictions. To summarize, model multiplicity gives us flexibility to choose between equally accurate models, and this may even lead to legal pressure for companies to search the space of equally accurate models to find the one that is the least discriminatory. However, the latitude of choice that model developers have, which model multiplicity highlights, also points to a necessity to justify why a certain model is chosen. Thank you so much for listening to our presentation. Please read our paper for the proof of the relationship between accuracy, variance, and multiplicity, implementation suggestions for model aggregation techniques, and much more detailed exposition of model multiplicity benefits and downsides. Here is a paper QR code and a tiny URL to our paper. Thank you so much.